Hey everybody, this is Larry. This is me trying to do an extra random algo problem that I haven't done before, just an extra day. I feel like today I'm a little bit more well rested than usual. And yeah, let's give it a go. Today we have 1265, print immutable linked list in reverse. Oh yeah, and this is July 29th, 2024. How the time has flown. Yeah. Anyway, yeah. So okay. So what's an immutable linked list? Okay, it's just a linked list that is not mutable, I guess. And you have only two things. You have get next and print value, and you want to print out. It's just a print, right? What? Print the. I mean, okay. So basically. Okay, I mean, basically, you want to call this function n times and then have a get next. Yeah. Right, to get the nodes. Okay. I mean, there are two ways to really do it from the get go. One is recursively, and one is recursively, the other is just like using a list things, right? Because at least in Python, I'll do both of them. I mean, of course, we have to think about the follow up, which we can do a little bit later. I mean, constant space we can always do just in general. If you want to do n square, which in this case is n is 1,000, that solution I'm not going to do because it's not as interesting. But linear time and less than linear space complexity is interesting. I mean, I could do like n log n time and n log n thing, but I don't know. But we'll think about that in a sec. So okay, let's just do the recursive thing first, right? So now we have head, right? So maybe we have like get and print next or something like this, right? Of a node, and then it's just so then we want to get the next node. Node is equal to node dot get next, maybe, and then we print it, right? Well, we get the next node, and then we print the value. So I mean, just basically this, right? And that should be good. Oh, I did. Well, yeah. I was gonna say this is gonna be infinite loop, but luckily it does not because of this thing. But yeah, if node is none, then we return. I don't know how I forget a base case, but guess that's fair. And also, I don't know why I wrote it quite like this way, honestly, but I guess we could do this way. Okay, there's at least one item, so this should at least work once. The way I wrote, I think I actually this is incorrect because I skipped the first character. Yeah, as I did. I don't know why. No, I think I prefer this here. To be honest. But it is a little bit more awkward as a result. No, it still doesn't. Oh, because. I don't know. I mean, this is an easy fix, right? It's just I'm trying to make it clean because here we just do head dot print value. I mean, I think the real way that I want to do it, which is why this is a little bit off, is because I want to use a sentinel value, right? So in theory, maybe I would have like a new head. That's how I always call my sentinel heads. That points to the head, and then I would just point a new head, and everything would make sense. But I think as a result of not using that, that's why like things are a little bit messy, right? But that's fine. That's okay. We could just do it this way. Give a submit. Yeah, I mean, this is pretty straightforward in a way. And like I said, this is going to be linear time, linear space due to the stack space that we get from putting on a stack. And of course, you can make, there are a couple of things you can do. You can make this implicit stack into an explicit stack, right? So here, maybe you could have you know, current is equal to head, right? While current is not none. So you have we could call it a stack. It doesn't. I don't know if that makes any sense. But yeah, current is equal to current dot next, and then stack dot append current, right? Something like this, or maybe before, right? And then while length of stack is greater than 0, because that's stack dot pop dot what's it called, print value, right? And that's really it. Yeah, so you could do it that way. It's the same thing. I mean, yeah, and you could see that in the same way. It is going to be linear time, linear space. Now, what gets interesting, of course, is that how do I do linear time complexity and less than linear space complexity? That is interesting. I don't know that I do. No. Let me think about this for a second. I mean, like I said, the constant. If you only care about constant space, you can imagine just do it at n squared, right? Like maybe you get the length of the list, and then you get the length of the list minus 1, and then print that one, and so forth. So that's gonna be n squared. So you could definitely do that. But linear time complexity, huh? And less than linear times linear space. I mean, because I think like one way that I would think about doing it is just with building essentially like a skip list type thing, or not a skip list. I mean, I guess maybe a skip list if you want to call it that. But also like the idea is that maybe you'll build, you know, links from basically like a divide and conquer thing, right? Like half of it and then half of that and stuff like that. And maybe you could do it that way. Then I think the peak space would be log n, but it'll be n log n times. So, how do I do this in linear time complexity and less than linear space? Actually, it's not super clear to me, honestly. I was just thinking about for some reason I was thinking about a sorting algorithm that that I remember seeing a long time ago. You know, there are a lot of random sorting ones, but one way that you could get sorting in a really funky way and is in a linear pass. I mean, I don't think this applies to this problem, but I think it's just fun to kind of think about. Or you know, maybe it's just fun for me, and I'm a nerd. But it's fun in that I'm just smiling a little bit because it's such a silly, funny algorithm where to sort you just make you make your own thread and then you sleep by the x seconds before popping it, right? So the idea behind that is that, and we'll just ignore negative for now. I mean, you could re-index, re-normalize, it doesn't matter, right? But for example, in this case, it would sleep 6 seconds before printing out a 6. It was 2 threads would sleep 4 seconds before printing out 4s. And, you know, and so in that way, you get 0s get printed first, then 2 4s gets printed second, and then a 6 gets printed last. So something like that, but I don't think that applies here. It is like just a really funny sort that I don't know, it just came to my mind for a second. But also not very practical. I don't think I've ever done it, but I remember reading it a couple of times, like separate times, and I'm like, that's really funky. But, and funny. I don't know, to be honest. Is there some funky things? Yeah, I mean, there is like a divide and conquer thing, but I don't know how to get that to linear time. Right. I think, okay, let me take a look at the clock. It's about 10 minutes into the video. I'll time bounding by about 5 minutes because I honestly don't want to spend that much time on linked list stuff. But yeah. And of course, I mean, I hope that there's nothing like funky, like changing. I don't think you're supposed to, I mean, it's immutable anyway, right? But I think like sometimes people consider like changing the links and stuff like that on a linked list is considered constant space. I'm like, no, that doesn't. So I don't know. Maybe if it's one of those, I don't want it to be one of those, because that's just, I don't know. I always consider not in the spirit of things, but um, I don't think I do know though. Because there really not that many linear time things in linked lists that I haven't heard of. Though. Could be wrong. Clearly, maybe I'm wrong. I mean, because okay, so linear time just means either you do one pass or constant number of passes. But I don't see how you 2 passes. Three passes? I don't know. Like, what are you gonna do with 3 passes that you can't do with 2? And with 2, I'm not quite sure. Like, you get to last. Yeah, I'm not sure. Alright. I said I would come gated, but I think I give up a little bit. So let's take a look at the solutions. Maybe see. Because I'm just not confident that they have a real solution. So recursion, that's what we did. Using stack, that's also what we did here, even though you could say it's not. Yeah, I mean, actually the code is pretty much the same. It's a little bit weird to call it a stack, but that's fine. I always forget about square root decomposition, actually. Okay, I mean, I guess so. Yeah, I mean, because the square root of, I mean, I guess it's very, I mean, it's exactly the same thing as how I would have described my n log n solution, but yeah, I guess the math works out. Okay. So I honestly I didn't think that it would Yeah, I mean, I didn't think that it would be something this crazy. Like, I mean, we've done square root decomposition before, so I'm not like, you know, but yeah, we talked about divide and conquer. I think that's n log n though. Yeah, constant space we can just do n square, right? Yeah, that's we also talked about that very briefly. Yeah, I mean, so we talked about everything except for square root decomposition, which I talk about a lot actually, but for some reason I didn't think about it for this one. Because then, okay, so each block, I guess so. Okay, yeah, I mean, I think it's a very cool idea that comes up randomly. Maybe I should have thought about it. I don't know how I feel about it. Because that is a very high-powered thing, so I'm not going to talk about it that much more for this video, but yeah, I don't know how I feel. You probably don't need to know it on an interview, but yeah. That's all I have for this one. That's all I have for this problem. Yeah, thanks for watching. Stay good, stay healthy, to good mental health. I will see you later and take care. Bye-bye.